Good morning, Riverside. So we are going to learn about sound today. This is the first of two sound videos. This will just be the first part of the notes, with harmonics being in a second video. I have turned on the subtitles for PowerPoint, but sometimes they can get a little finicky, so I will try, if I catch it, to re-speak, but we will just wing it and hope for the best. So, as you guys learned last time, in the last unit, sound is a specific type of wave, a longitudinal wave to be exact, and it has compressions and refractions in the matter. So, as things are vibrating, it's creating pulses that are leaving that vibrating object and creating sound waves. As you guys know, those compressions are that dark area, that area of compression where all the atoms are compressed together, creating a high density area. Then the refractions are the opposite. Those atoms are spread out a little bit. So they are that light area, less density. So the speed of sound is not like the speed of light. It actually will change. The first part that it will change on is due to temperature. So think about yourself. In the summer when it's warm outside, do you want to play outside? Do you want to go to the lake, do jet skis, all that jazz? So in warmer temperature, you have more energy, okay? You have a faster speed. Then think about yourself in the winter, right? Most people tend to feel like they need to hibernate, okay? Colder temperatures have less energy. When you have less energy, you're going to have slower speeds. So the speed of sound in air is a little bit over 300 plus or minus 0.6 meters per second for every degree Celsius. So for example, if I have something that is 2 degrees Celsius, I would take that 0.6, multiply it by 2, and get 1.2. Because that was a positive 2 degrees Celsius, I would add it to make 331.6. If it was a negative 2 degrees Celsius, then I would subtract it. Water travels a little bit faster. It's a little bit less than 1,500 meters per second with a larger variance for temperature. And last, we have steel at 3,225. Okay, so what you're noticing on the trend, or what you should be noticing, is that things that are denser have faster speeds. The more dense the material, the faster speed sound will travel through it. So this is where, if you've ever heard of like more of the bluegrass, where they take a saw and start to play it, and that's when you hear that kind of more high-pitched music. It doesn't quite sound right. That is because the sound is traveling faster through the steel than it is through the air, giving it that high-pitched twang that a lot of them love. So a Doppler shift happens when there is motion. So either the thing that's making the sound is moving or the thing that's hearing it is moving, but one or both need to be moving. So for this example, we're going to experiment with a train. Now, what's weird is that Doppler shift is something you've been doing your whole life. Okay? By playing this next sound clip, you're going to know what happened without me having to explain it. So let's listen. So the first thing I'd ask you is what happened? Normally, most of you are probably sitting there going, a train approached you and passed. Now, why is it that you knew that the train was heading towards you? Yes. Okay. Volume. It got louder. But also, what did you notice after it approached you? What happened to that sound? If I play it again, could you tell me the exact second it passes you? Yeah, did you hear that drop? There was a drop in the tone. That's exactly when it passes you. And this is something that you probably did in your head without really noticing why. When the train is heading towards you, it gets higher pitched, right? The minute it passes you, it starts heading away rather than towards. So that drop in pitch is noticeable. So why does this happen? Sound waves emulate in all directions, in all 360 degrees. Now, in some cases, this isn't exactly true because things interfere. But when it first starts, it does begin in all directions. So, for example, me talking right now. My voice box is putting out sound in all directions, but the shape of my throat and my skull is blocking it in most directions, which is why if you stand behind me, I'm not going to sound as good. You're going to have trouble hearing me, and I might sound softer. Most of that is due to ear interference with my head. But if we have a plain, normal sound and it's able to propagate in 360 degrees, this is what it would look like. Now, Doppler shift happens when something is moving, and as you just saw from the text, it would either be compressed or expanded, depending on which way you are listening to it. So if you notice that orange dot is now moving. On the right side, what do you notice is happening to the waves? Right, they're getting closer together. This is a compression. Those waves are happening more frequent than normal. What do you notice about the left side? Right, it's further apart, which means that that is becoming a refraction. Waves are happening less often than if it had just stayed still. If you notice, I said things like compression and refraction. That is because we are still talking about a sound wave. However, in this case, we need to start focusing on frequency. So the right side, the waves that are hitting the edge of the picture, are they hitting more often or less often than when it was standing still? Right, on the right side, it's hitting more often. It's more frequent. So instead of saying, let's say we have a 2 hertz sound, now on the right side, it might be up to 4 because it's hitting twice as many times as it was before. On the left side, okay, if we started with a 2 hertz sound, we might be talking about a 1 hertz sound because it's only hitting half as many times as it had before because it's spread out more. That change in frequency is what we hear in the sound. If something has a higher frequency, it has a higher pitch. When that train passed us, it started heading away, which means we had a lower frequency and a lower pitch. That's where we hear that drop. Now, this also happens if the listener is moving. So now we have a source, and the listener moves towards and away. While the listener moves towards the sound, she's hitting those waves more frequently. Okay, so think about it like a track. If you had lines on a track and you need to know how many times you hit, like let's say 2 feet, right? If you're just walking, you're going to hit 2 feet every half a second. Okay, but if you start running, you're going to start hitting those increments a whole lot faster. The same thing goes here. When she starts moving away from the sound, she'd slow down how many times she hit the wave. So for us, it's when any relative motion happens, the sound or the listener or both. If the sound and the listener are moving towards each other, it's going to increase the frequency even more. If the sound and the listener are moving away, you're going to experience a lower frequency. If they do it together, it's going to get even lower. Think about it like throwing a baseball. If you throw a baseball towards someone in the outfield, back and forth, then they move closer. You don't have to throw it as hard, and it'll get to them as fast. It'll get them faster than where they were before. If they back up, right, it's going to take longer for that baseball to reach them. If they do it over and over and over again, less and less time if they're moving towards you, or more and more time if they're moving away. That's how we deal with radar. So you guys are used to it in terms of weather, so that's what that animation is, or for the police. So that animation is showing a radar wave. It is leaving a dish, hitting a water particle, and heading back to the dish. Now, if that radar wave goes out, hits the water particle, and comes back and does it at the same distance or the same frequency every single time, it always takes it 2 seconds. That water particle isn't moving. But if it's taking it more and more and more times, so the first time it goes out and back, it takes 2 seconds, then it takes 3 seconds, then it takes 4 seconds, that water particle is moving away from the dish. If it takes less and less time every time, so the first time it takes 2, then it takes 1, then it takes half a second, that water particle is moving towards the detector. Depending on how different it is, we can tell how fast that water particle is moving or how fast that storm is moving. That's how we can tell at what point it's going to rain in our area, is by how fast those individual water particles are moving. Same thing goes for police radar. The radar comes out of the detector, hits your car, and comes back. Dependent on whether or not the time is getting less, you moving towards the detector, or the time is getting more, you moving away from the detector, it can tell how fast you're going by how much it changed. So resonance. Every object has a natural frequency. It's kind of weird to think about, but think about it like your favorite song. If your favorite song comes on the radio, right, you have a connection to it. It sparks something in you. Think about that when you think about natural frequency. Every object in the universe has its own favorite song, so to speak. Now, if I have a tuning fork sitting out in the middle of the room, and I find something with the same frequency, the same favorite song, and I start playing it near it, well, then they got to jump in, right? Came on the radio, you start dancing, you start singing along, you can't help yourself, right? Same thing happens here. If you have something that's the same frequency and it gets placed next to that one that isn't moving, it starts singing along too. This is actually how a car's radio works. So when you set your car radio to, let's say, 900, okay, and there is a radio station at 900, that's when you get that crystal clear radio connection. But if the radio, let's say 99.5, right? If the radio station's at 99.5 and you set your radio to 99.6, okay, it sounds fuzzy. It doesn't sound right. That's because you're not quite at the natural frequency. If you're both exactly the same, then that's when you start singing. That's why your speakers start playing the same music that's coming out of the radio. So, some examples of resonance beyond the radio that we just talked about. So, there's a folklore about a wine glass. If you hold a wine glass out and you are skilled enough in singing, especially for like opera, and you play a specific note at the right frequency, and loud enough with enough power, okay, that wine glass will break. I'll show you that in a second. There's also swings. So for example, if you sit down on swings, you can't kick your legs all willy-nilly. It doesn't work, right? You have to kick while you're going forward and pull back when you want to go back. And there's a timing to it. If you don't get it right, the swing doesn't work. That's a natural frequency. How many times per second do you need to kick or retract your legs? And there's a timing there. That's a natural frequency. Also, instruments, when they hit a natural frequency, that's when we get those notes. That's why every piano that plays middle C sounds the same if they're tuned correctly. They've all hit a natural frequency at that note. The last one is the Tacoma bridge collapse. That one is going to be easier to explain in the video. Alright, so I apologize now. The wine glass is a little annoying. I'm going to keep it small so that the subtitles will still be on. What you're going to notice is that the MIT grad, he is going to figure out what the natural frequency is by messing with the wine glass to begin with. Then he's going to play the same song back to the wine glass, or the same note, and the wine glass will start to oscillate. And again, I am extremely sorry. This will get loud if you want to turn down your speakers. So now I'm going to mute the video. So while he's playing the sound, right, the wine glass hears its favorite song, it starts jamming out, it starts oscillating. Now it's vibrating to the same frequency that the sound wave was on. So here you can really see it wiggle. Now, is glass meant to bend like that? No, not at all, right? That's why it breaks. It's not meant to do that. It can't help it, but when it gets to a certain point, it just wiggles too far and it has to break. Same thing goes for the Tacoma bridge collapse. I'm going to skip around in this video, but this happened a little bit after it was built. Okay, this bridge was it was a big engineering feat. It was one of the longest that had been built at the time, and it was built over a canyon. Everyone was real proud of it. Okay, shows them driving over. Well, a couple months later, the wind in the canyon began to hit the bridge pretty severely and at just the right frequency. See it there wiggling, just like that wine glass. So the wind started hitting it at just the right frequency. It was its jam, it was its favorite song. So the bridge had to start singing along, had to start dancing, grooving. And if you notice, it's really wiggling. That's actually a full car that's sitting there. It's getting pretty big. Now, steel and concrete are not meant to do this. They're not meant to bend. So later on, it couldn't help it. It just had to collapse. Fell everywhere. $6 million dumped into the river. Now, on the plus side, this gave us a lot of engineering. A lot of building codes changed after this. Bridges are no longer allowed to be made this way. There are a lot more reinforcement in the bases and the way that the top structure is hung. So everything has a natural frequency, we just need to find it. Now, human hearing. Human hearing is when sound waves interact with our eardrum. Okay, those compressions and the refractions pull or push the eardrum back and forth. So you have the red compressions pushing the eardrum and the blue refraction pulling the eardrum. That wiggle is what causes disturbances in our inner ear fluid. That inner ear fluid causes the bones that are inside your ear to vibrate. Now, your notes have a much better picture of this. But right here in the inner ear, okay, we have the eardrum right here. Then we have the hammer, the anvil, and the stirrup. Those are the 3 bones located in your middle ear. Now, those bones vibrate, and that pushes pulses into what's called the cochlea. That's a snail-looking thing. Those hairs in the cochlea vibrate, and that vibration causes nerve signals to head to your brain. Then your brain detects those nerve signals, decodes them, and tells you what sound you heard. You have a couple million hairs in there in that cochlea. However, whatever you're born with is what you got. So if you listen to anything on a really loud or for a long period of time, you can rip those hairs out. And once they're ripped, they're gone. Okay? This is also where you might have heard things like a cochlear implant. Usually people that are eligible means that the rest of their ear functions fine, but they either don't have hair in their cochlea or the cochlea itself is damaged in some way. So what they do is they put in a little receiver right here that's meant to wiggle, and then they connect that directly to the brain and take the cochlea out. Humans at birth can hear from about 20 to 20,000 hertz. The minute you're born, this starts changing, obviously, depending on your hearing being damaged. Usually in your teenage years, where you are now, you still have quite a bit of that. You probably are within 18 to 19,000 hertz. Unless you listen to headphones a lot, then you're probably down in the 16 to 17,000 range. Headphones are extremely dangerous to your ears because they don't allow the sound to dissipate. Okay. Sound is meant to go out in 360 degrees, but what especially earbuds do is they take all 360 degrees and funnel it into that one little area going directly into your ear. So think about it kind of like a magnifying glass out in the sun. When you have a sunlight going through the magnifying glass, it focuses it into a specific spot, and that's when you get that heat. And you've seen like a lot of cartoons where they fry an ant or something like that on the ground. That's what's happening to your ear with earbuds. Also, I have to go science teacher on you. Earbuds also increase the amount of bacteria in your ear, and that's just nasty. So if you can, get over the ear headphones if possible. So sound intensity. The intensity is based off that amplitude. So remember when we were labeling waves and you had to label the amplitude, but we didn't really tell you what that was. What that is saying how strong something is, how loud that sound is. That's its amplitude. The bigger the wave, the louder it is. The SI unit for intensity is decibels, or a little d and a big B. It's a logarithmic scale, meaning that it's not your normal linear. So 20 is actually 10 times louder than 10. What you're going to do is say how many groups of 10 are between the two numbers, and that gives you how many zeros. So let's try some. Here's some common decibel levels for you. So if you notice at the bottom, our threshold of hearing is at 0. A whisper is at 20. Those are 2 units of 10 apart, 10 and 20, meaning we would add a 1 and 2 zeros, 1 for each unit of 10. So that means a whisper is 100 times louder than the threshold of hearing. Let's try another one. A buzzing mosquito is at 4 decibels. A busy street corner is at 70. 40 and 70 have 3 units of 10 between them. That means we have a 1 and 3 zeros, meaning that a busy street corner is 1,000 times louder than a buzzing mosquito. Try one more. So we have a rock concert at 110 decibels. A busy street corner is at 70 decibels. There are 4 units of 10 between a busy street corner and a rock concert. So we would have a 1 and 4 zeros, meaning that a rock concert is 10,000 times louder than a busy street corner. Beats. So our brain does something weird when things are kind of close, but not really. So a beat is when there's a difference in the frequencies. So here we have a wave that is up while the other wave is up. And these two waves are very close together. So these would make constructive interference and we would get bigger wave. But because their frequencies are not quite, later on we have an up while the other one has a down. That's destructive interference. So they cancel each other out, meaning we have nothing left. And again, up and an up. So we have constructive and it gets bigger. Doing that repeatedly gives us that beat that we hear. Now this is actually becoming more and more frequent when you're talking about like EDM music or digitally recorded music, is that a lot of times beats are not reliable if made by humans. So rather than pressing, like let's say the space bar over and over and over again at the right beat, a human can get off. So what they do is they play two sounds that are very, very close, but they're slightly different in their frequencies. And that creates a natural beat. So let's try. These waves are different by 1 hertz. How about 3? That's roughly about 12. So when you're talking about a beat, the beat frequency, or what you're going to hear, how many waves per second you're going to hear, is the difference between them. So if we have 400 and we have 402, the beat frequency is going to be 2 hertz. Okay, and the last thing for today is the quality of sound, called timbre. So this is why if you play a middle C on both a piano or a trumpet or an oboe or a cello, they all sound different, but they're all playing the same note. They're playing the same frequency. So the same fundamental frequency. But what we're doing is we've changed the combination of harmonics and their intensities. So for example, here's a trumpet. Now I'm going to play the same sound, but I'm going to take the first 2 harmonics out of it. That's where we get more of that oboe sound. Now, what if we go back to that same trumpet sound, but this time I take out the even harmonics? Now we have our clarinet. So each and every one had a frequency, the same frequency. But by messing with the harmonics and how loud certain harmonics might be in relation to each other, I changed what instrument we were talking about. All right, guys, so what's left in your notes is harmonics. I've made a separate video for that. That way you don't have to go back and forth between the two. If you need help in any other area, please make sure to go back and visit the YouTube channel for more. Thank you for joining me today, and I look forward to seeing you in class.